All right, so the first thing we're doing is calculating CN beta fin. So this is the vertical tail effect on CN beta, the yawing moment due to beta. So we need the distance to the vertical tail aerodynamic center, which is here. And so the distances on the figure are labeled like this. And so you add them together. We calculated this in part one, along with the, let's see, no, this is the number, that's the root chord of the wing. So you just get that number and you add them all together to get the total distance. And so you should get that. Did everybody get that? Yep. You have to go back and look at the root chord of the wing. I'm forgetting what it is. Somebody know what it is? 12.7? That's from a couple homeworks back. We just calculated this in part one. So you add all that together and get into the formula for V sub V. It's the ratio of the areas and the lengths. You should get that. Check. Then you go into the formula for CN beta fin, and you stick all that in. You should get 0.2271. You need V sub V for that. You need the lift curve slope that you calculated in part one. You need the airspeed ratio, which we said just use 1, and d sigma by d beta was 1, right? That was 0.08. So that's just plug and crank. Questions on that? How about on Zoom? Everybody good? No response means yes. All right, so we want to calculate CN delta R, which means we need the effective lift curve slope of the rudder. This is how much lift we get per degree. And so that comes from the appendix and the charts. And you need the 12% airfoil, thick airfoil. And it's a 30% chord rudder. So this means you need to look up a thickness to chord of 0.12 and a flap chord to total chord of 0.3 on that chart. So that gives you the data to look on the chart. So there's the chart. Make sure you mark the points you picked. The 0.3 is the 30%, and you go up to the 0.12. It's because of 0012, and you go across and you should get like 4.5 something. So make sure you show the chart, show the point, because you're going to get credit for showing the point on the plot. Oh, let's see, I need to share that for the Zoomers. Sorry about that. Let's share that. Now we're sharing. Get the chat out of the way. So again, now that I'm sharing, show the 0.3 pick down here. That's the 30% chord. Go up to the T over C line of 0.12, and that's from the T over C here. Grab the 0.2, pick off 4.5 something. Make sure you show the value and show the chart. Then you go into the formula. To get AR. So that's the point that you're picking the CL subscript delta. It comes from this. And then you go into the formula that's on page 322. You should get an AR of 2.699 per region. And you go into the formula for CN delta. And so what that does is that goes into the formula for the total yawing moment of the airplane. Of course, you have to add in other yawing moments. We'll talk about the yawing moment due to aileron and the yawing moment due to beta we've already talked about. So you just have to add them all up. Questions about that problem? And as you've seen before, these charts that you have to look stuff up, they're generic wind tunnel data charts. They're made, notice that one contains a whole bunch of different airfoils in it. So you have to look up the airfoil thickness. So if you had a 0009, you'd look up the value for that, the 0.09. And if your rudder happened to be 50% chord, then you'd look up on the bottom axis the 50% line. So this chart works for a lot of different airfoils with flaps. So we could use this for the elevator because it's an airfoil with a flap. But we're doing a rudder right now. Okay, questions on that one? Everybody good? And then the last one is a derivation. I'll just stay on the same board. You guys have had a chance to get this down, right? Sorry, I forgot to silence my phone. So on this one, draw this picture. I'm going to check for it. Everybody get that? Draw this picture on your homework. Shows the rudder with a positive deflection. There's a side force. And so the rolling moment, let's use script L. The rolling moment is going to be the side force times the vertical moment arm. So we're not using LF here because we're talking about the rolling moment. So we need the vertical moment arm. So if you want to draw another picture, this would be good to draw of the fin like this. This is a side view showing that distance. Why did I put a plus sign here? Axis is forward. Curl your hands. So a positive Y gives a positive rolling moment as long as the fin sticks above. Is there any reason why we don't have the vertical tail stick down? We could, right? So picture this. Here's our airplane. What do you think about that? Anybody see a problem? Yeah, you're going to hit the ground with the vertical tail, right? And the other reason is that we get the correct CL beta to roll away from the side slip, because we want a negative roll. Again, this is not anything to do with stability. This is the roll due to rudder, and it's just the effect that you get from the rudder. It's the pilot control, not stability. So this gives you the moment arm, and then you need to do the side force is the CL due to the rudder times Q infinity SB, and then you move forward from there. Remember, you're going to turn this into a coefficient, so you're going to divide by Q bar SB and go from there. All right, my bad here. Sorry, this is the lift due to the rudder, so this has got to be multiplied by 1/2 rho V sub V squared SF. And again, the derivation of this, I'm not going to go through in detail because we did it already. The derivation of this is exactly like for Cn delta R. The only difference is this moment arm and the sign. So go back to your notes from last time when we did that. Yeah. This what? No, that's the velocity sub F. Yeah, and that's confusing. Again, for writing this book, I would use something different. Yeah, V sub F is the volume ratio for the fin. This is the velocity when it gets back to the vertical tail. So make sure you show through this work, you show the dividing by Q bar for the total airplane, just like we did for Cn delta R. Go through the same steps that we did and you're good. Yeah, somebody commented the Predator has a downward facing vertical tail, and it does, and has that long landing gear on it. Okay. So back to the lecture, we were talking about CL beta. And as we just talked about, we want this to be less than 0 because we want the airplane, try to throw out a 3D version of this. When we're in a side slip beta, we want the airplane to roll away from the side slip. Remember, we talked about the airplane. I left my foam airplane upstairs. But if the airplane starts banking like this, it's going to fall, and you want it to roll back upright. So the number one contribution was the wing dihedral. And you can do some chase around charts for the entire effect of the wing, dihedral versus the dihedral angle. So if you go to appendix B.9, page 341, there's some charts there that allow you to estimate that. Okay, number 2 effect is the wing position on the fuselage. And really this comes down to high wing or low wing. So let me draw a picture of that. So we're going to draw an aft view again. Here's the fuselage. Here's this air coming in from the side with the side slip, so that's the right side of the airplane. Let's look at a high wing. So we're going to put a wing across the top of this thing. Right? Are you picturing the airplane now? We're looking from behind. There's the wing on top. The flow that comes in goes around the fuselage like this. So picture a bunch of flow arrows going around like this. And you notice that the flow is as it goes around the fuselage, pushes up on this side of the wing. So we get more lift here. And on this side, we get less lift. So we get a positive delta on the right and a negative delta on that. So that pressure difference, the lift difference, is going to give us a negative roll. Let's see if this marker works. So what if we had a low wing? It would be invisible. So here's our low wing. Can you see you'd get the opposite effect? The flow's coming down on this side and up on this side, so it tends to roll the opposite way. So for the high wing, you'd get a CL beta in the stability direction, whereas for a low wing, you get the opposite. Now remember, that's just the wing position, so you still have the dihedral effect. So if you have a lot of dihedral and you have a low wing, they tend to cancel each other out, and you might get enough dihedral effect to overcome the low wing. And then the other effect that they found out was when they started sweeping wings, that if they had a lot of wing sweep, they got another effect due to CL beta, another roll due to beta. And so this is number 3. So I'm going to draw a wing that's really highly swept. So here's our wing, like that. I did pretty good getting that symmetrical, didn't I? So here's, I'm going to draw a lot of beta here to exaggerate the effect. So there's the front of the airplane. You notice that when there's side slip, the airflow here pretty much comes into the wing perpendicular to the chord. Whereas over here, notice that the flow is pretty much span-wise. It's not really going over the airfoil of the wing. It's kind of just going down the wing. And because of that, we get more lift on this side because you get more flow across the airfoil. Whereas on this side, you don't get a whole lot. You get a loss of lift because of that span-wise flow. So again, with wing sweep, you'll get a stabilizing CL beta. Now, it turns out for some of the dynamic stability that we'll talk about later on, you can actually have too much CL beta. You have too much stability in bank, especially for like a fighter aircraft, and then maybe it's resistant to side slip so much that your roll rate is not, you're not as maneuverable. And so for an airplane like the F4, when they built it, it had so much wing sweep that they got a lot of CL beta from that. So they actually put a little anhedral, the opposite of dihedral, into the airplane. The wings tend to droop down a little bit so that they got the right amount of CL beta. So all of these effects go in. And then the last effect is the vertical tail. And this derivation looks exactly like the one we did for Cn beta. But again, the only difference is the vertical moment arm versus the horizontal moment arm. So what's going on here is that let's draw a side view here. There's the CG. Back here's the vertical tail. There's the AC. And the moment arm we're interested in here is that vertical one, not the distance back, because this is the yawing moment. And then if we do a top view down here, like that, there's the aerodynamic center. And we've got beta coming in like this, reduced by the side wash, just like we did before. And so we're going to get a force, a lift force, due to beta in that direction. And just like any other aerodynamics problem, we're going to take the lift curve slope of the times the angle of attack, get the lift, and then multiply by the moment arm. So if you want to draw that vector in here, it's a vector that's coming out of the page here in this direction like that. Notice we can put an F on here for fin. So the rolling moment, and now I'm going to use a script so that we're not mixing up lift and lift. So this is rolling moment. Although often in text and writing, you'll see just an L here as well. So it's going to be the lift of the fin times Z sub F. And we look at our picture, and the way we've drawn it, with that angle of attack being beta minus sigma, it's going to push that way. The vertical tail is above, so it's going to roll it negative, right? Positive roll is this way, and we're going the other way. And so we build up the lift of the fin aerodynamically. So this is the exact same derivation. And in fact, it's the thing that you had in the rudder derivation that you're doing on the homework, except here, well, sorry, yeah, the CLF then is generated by the rudder rather than the angle of attack. So that's where you get AR times delta R, because you get some lift due to the rudder. And we could even include that effect here if we wanted, right? In the roll due to the rudder, that's what you're doing. If you have that positive rudder deflection, you're going to force this direction, which is into the page there, which is in the positive direction here, times that moment arm. So all we need to do to complete this is to fill in what CLF is. Let me do that over here in the wing sweep section. All right, so CLF is going to be given by the angle of attack, or sorry, the lift curve slope times beta minus sigma. So that goes into there. else I got? I gotta remember to get my 1/2 rho v sub f squared SF ZF, and I've got to grab the minus sign, right? So the lift coefficient comes from lift curve slope times angle of attack. That goes here. There's the rest of the stuff that turns lift coefficient into lift force. So this is the total force here times the moment arm. And now we have to turn it into a coefficient to get CL. So we divide this whole thing. Could I do this all in one step? We're dividing by 1/2 rho v squared S B. Does that make sense? Is this too confusing? We're just going to divide that whole equation by that, right? So then CL, the rolling moment coefficient, is going to be AF beta minus sigma. The 1/2 cancels, the rho cancels. We get our V sub F over V squared, just like we did last time. We get the SF over S ratio, and we get the ZF over B ratio. And this should look really familiar because everything is the same that we had for the yawing moment. The only difference is the moment arm. And the sign could be different. So CL beta is just the derivative of that thing. And maybe you're sitting there and saying, yeah, I'm getting tired of writing this thing. What are we going to call this? Well, that's a volume ratio. Problem is, we've already used V sub V. We've already used V sub H for the horizontal tail. Of course, that doesn't make sense for this. We've already used V sub F, right? So what are we going to use? Nobody has really defined this as a ratio. I mean, you could call it V sub F 2 for the second one or whatever. But let's just carry it along like this so that we don't get super confused with all the V subscripts. Because we're already there already, right? And so in reality, I've actually sketched out the homework for you because all you're doing is replacing this with A sub R delta R, and that's the lift due to the rudder. Make sure you get the sign correct on that. So it's worth going through this again. CM alpha gives pitch stability, and L gives pitch trim, or pitch control. So this is the stability, this is the control. What we've just talked through now is CN beta gives us yaw stability, and the rudder gives us yaw control. So we've added another axis. There's 3 axes, so we've covered pitch, we've covered yaw, and now we're doing roll or bank angle stability. And the control that people put on the airplane to control bank is the aileron. So that's the last thing we need to talk about. These have to define what's the positive elevator just by convention, what's positive rudder and positive aileron. Those are arbitrary. This stuff is not. This is, we have a pitch in the correct direction to reduce the disturbance. We have a beta disturbance, we want to yaw in the correct direction to reduce the disturbance. Beta disturbance, we want to roll to reduce the beta. So that's, all of this is determined by the static stability criteria. So, what's positive aileron? So, draw a wing. Looks like this. Draw your wing first. I want you guys to draw this. I'm not going to ask you to turn it in, but it would be to your benefit to draw this. Because if you draw it, it goes into the different part of your brain and it sticks. Well, my airplane's going to flip because it's not symmetrical. So let's make the wing a little longer here. Does that look better? All right, so ailerons are flaps that are added outboard so that there's a long moment arm to allow this flap to act. Got to get my art right here. All right, does that look like it's deflected upward because of my hidden line there? So that's a flap that's deflected upward. And then on this side, we're going to add a flap that's deflected down. So this is up, down. So far, so good. So now a hint, a tip, a suggestion. If I ask you on a quiz or on a homework to draw ailerons deflected positively, you would draw this and you would put up and down on there so that I knew for sure that your drawing was showing me what you really intended. Make sense? So you would draw it and label it. So what does this do? This is reducing the camber on the section of the airfoil with that flap so we get less lift. And we're going to get less drag, and that's going to be important in a minute. And then how about over here? The flap goes down, so we're going to get more lift. And we're going to get more drag. So which way is the airplane going to roll? That wing's going to go down, the left come up. Is that positive or negative? Right-hand rule about the x-axis, this is a positive rolling moment. Which way is the airplane going to yaw? We got a shorter drag vector over here and a longer drag vector over there, right? It's going to yaw nose left. We're going to get a negative yawing moment. So is the rolling moment a good thing? Or a bad thing, and we don't care? Why did we add the ailerons? To roll the airplane, right? So the rolling moment, this is just convention. We've defined this to be positive. So in this convention, a positive aileron gives a positive roll, and that's good. It's not really good or bad. It's we get a rolling moment, and by convention, that's what we get. How about the drag? Positive aileron gives a negative yaw. What do you think about that? Good, bad, we don't care. Is the aileron a yaw control device? No, the rudder does that. So, is this good or bad, or we don't care? Really, this is a side effect. This is the intended effect. This is a side effect. This is like the stuff you hear on the drug commercials where they spend 30 seconds telling you how great their drug is, and then 30 seconds telling you that it may lead to nausea, vomiting, diarrhea, hair loss, or even death. That's the side effects. You've seen those, right? So it's a side effect. So is this a good side effect or a bad side effect, or it's just there and we don't care? What do you think? It's just there. So we have to go beyond just rolling the airplane, and we have to think, well, why would we roll the airplane to the right? Because we're having fun, right? We're just going to fly around with a bank and go wee and bank the other way. No, we're probably going to turn to the right, huh? So you're going to bank, pull on the stick and turn. How about when we bank the airplane like this and it starts yawing that way? Kind of seems backward, doesn't it? We're trying to turn this way and we got our airplane yawing. So this is a bad side effect. We're yawing away from a possible turn. That's not a stability thing, it's just a side effect of the aileron deflection. And it's called adverse yaw. So you could write that down instead of saying bad side effect. People have a fancy name so they sound intelligent. It's adverse yaw. How are we doing on time? We got some time. All right, so what I've drawn up here is what I call the Roscom US Convention. If you look in your textbook, it's the opposite. You go, great, which one do I use? We use the one that I tell you to use. Or you check with, when you're reading a paper, what they define as positive aileron. So the other version that's opposite in your textbook, so the Aitken text convention is positive aileron produces negative roll and positive yaw. It's still adverse yaw because when here you bank to the left and turn to the left and you get yaw the other direction. So again, which one do you use? I will specify. Say we're having a quiz. I say draw in on a wing, deflected to produce the Roscom positive convention, and you draw that one. If I say draw them to produce the positive Aitken textbook convention, you draw it the opposite. This one will be up and that one will be down. Make sense? So I will very clearly say which one. Let's see what else. I'm used to this one because this is the textbook that I use in 714 and it's the one I used in undergrad. And this is how most people in the US, I don't know whether this is really the British convention. I think maybe Aitken is Canadian or British, and so it's the other way. So if you go work for an airplane company and you're working on something related to the ailerons, you need to ask what convention that company uses for their aileron. Well, this makes more sense, right? Because with our axis system, this is a positive roll. Positive ailerons, to me, should produce a positive roll. While we're talking about side effects, I don't know if we did this with the rudder, did we? I'm going to draw an airplane here with a positive deflected rudder. Did I do very good? It's kind of crappy. So with the rudder deflected like that, positive rudder, which way does it produce as far as yaw? Let me draw a top view. Right, that's what this is by definition positive rudder, right? So which way is it yaw the airplane? Give me negative. So positive rudder produces negative yaw. And that's just how it's connected up. Which way does it roll the airplane? Look at that picture or that one, it's going to roll it positive, right? That's a side effect. And this is part of what I was talking about way back when I said that lateral directional is easy because there's no trim, but things are coupled. Here we get these side effects between roll and yaw with the roll control and roll and yaw with the yaw control. So you get a side effect here due to the rudder. And here it's not so obvious whether it's good or bad. It just means that when you yaw the airplane, you get a little bit of roll and you got to remember to counteract it with some aileron. Unless something happens to your ailerons and they break. Then you can use the rudder to bank the airplane. And that's a redundant flight control, which can come in handy if something happens to the ailerons and you need an additional flight control. It gets more complicated because you deflect the rudder and then the airplane rolls and yaws, and so you get some side slip and then you get some roll due to the side slip. So it's a balancing act, but you can fly an airplane. And I've seen gliders, real simple radio control gliders built with no ailerons because they didn't want to put another servo on there. And they used the rudder to bank the aircraft. And it works fine, it's just there's some lag and you don't get as precise control. We talked about this in a class, gosh, it was probably 15 years ago, and talked about redundant flight controls. And the next class period, a couple students come back and they go, Dr. Steck, we went out flying because they were pilots. And we found out that when we opened the right window of the airplane banked to the left and vice versa. And I said, well, that's really cool. So there's another redundant flight control. Obviously, it's kind of slow, right? You open the window and then slowly you bank. So you wouldn't want to trust that for landing, lining up with a runway, but it happens. All right, I'm going to show you another roll control device next time after the quiz. It's called spoilers, and it helps solve some of this problem with the adverse yaw. Again, as a reminder, remember to go to Blackboard and look up your new room assignment for the quiz on Friday.